Welcome to the 6.2 Notes in AP Calculus. Our goal in this video is to approximate a definite integral using geometric and numerical methods. If you'd like to pause the video, you can see what we're going to learn. In 6.1, we use known geometric formulas to find the area of regions enclosed by the graph of a rate of change and the horizontal axis. And this was easy when we knew the formulas such as rectangles, triangles, and semicircles. Let's consider some other function f of x where the region is not going to be a standard geometric object. So for example, you can see I have x equals a and x equals b. If I were to draw the vertical lines from those two x values, x is a and x is b, and then bound the region by the function of the graph, or graph of the function rather, and the x-axis, you can see that the region enclosed would look something like this, which is not a typical shape. So your first instinct might be, well, is there a way to find this area using formulas I do know? Right? The easiest one I know is for rectangles, and perhaps you can draw a rectangle like this that fits underneath, and you can find the area of these two green rectangles I just drew, and that would be one approximation of the region. It might be a problematic approximation because you can see we left a lot of the blue highlighted area behind. So maybe we try making rectangles that are actually a little bit taller than the graph, like this. One advantage here is you might be able to find those areas more easily because you can see the first rectangle I drew has a height that is easy to see. It looks like two of these unit boxes. But you can see that now this is also problematic because these pink rectangles actually have a little bit more area than I need. This would be an overestimate. And we'll talk about this as we finish the lesson. But anytime you use rectangles to approximate the area of some kind of region, we usually call that a Riemann sum after a German mathematician. A Riemann sum is an approximation of area using a finite sum. And typically we can break regions in, or partition regions, into rectangles, trapezoids, or other shapes whose formulas we can calculate. And so we could use rectangles, we can use trapezoids, sometimes we'll use semicircles, or even there's something called Simpson's rule, which we can use parabolic sectors, which is a wild one. But either way, we can use these smaller shapes that we know the areas of to approximate the area of the region. So in our first example, we have the task of finding the area between the graph of this function, which I apologize, I don't know if I typed it in your notes, but that is the equation of the function, negative 1/12 x squared plus 3. We need to find the area between that graph, the x-axis on the interval from 1 to 5 using a rectangular Riemann sum, so that's telling us we're using rectangles with 4 subintervals. Okay, so let's go ahead and break that down a little bit. That's a lot of language. First, we know we're using rectangles between 1 and 5, so I might draw a vertical line from x equals 1 and a vertical line from x equals 5 and stop at the graph of the function because we're bounding the region with the graph of the function and the x-axis between these two x values. So the region in question, I'll color in green, that is my target. I want to know how much area is here because like you learned in 6.1, if this function is the graph of some rate of change, finding the area will accumulate that rate to find out the net change in units after some time. And so in this case, you see there's two boxes, a left Riemann sum and a right Riemann sum. We're going to use rectangles here, and in fact, we're going to use 4 of them. So 4 subintervals in this indicate that there are going to be 4 rectangles. Now, I wrote rectangular here, but if you don't see the word rectangular, you can just assume most of the time we're going to be using rectangles. Okay, now let's talk about left and right Riemann sums. Okay, a left Riemann sum is going to be using the left edge of the rectangle to determine the height. So if I draw a picture here, the left edge of the rectangle up top there will determine how high you go. Whereas a right Riemann sum, it's going to be the right end of the rectangle that determines the height. Let me be more specific. Let's let left Riemann be orange and right Riemann be blue. So if I draw rectangles on this graph, we're going to need 4 of them. Okay, so to find out how wide they are, we can have any width that we want, just like we did in 6.1. You can kind of break this up into, little rectangles like this maybe, or like that. It doesn't really matter. You can even do like some half rectangles, but really it's advantageous if we just use the standard width that every rectangle would be the same width. So essentially what I'm saying is we're going to break up this interval from 1 to 5 into equal sized pieces. In fact, in this case, 4 equal sized pieces. So the width of the rectangle in general, for other problems, can be thought of as being b minus a over n, where a is the start of your interval, b is the end of your interval. Typically a is less than b, so we have some interval from a to b, where a is the left end point and b is the right end point, and I want to find the distance between them, which is just a subtraction, b minus a. And then n is going to be the number of rectangles. Number of rectangles, okay? So in this case, we will take 5, the right end point, minus 1, the left end point, and we're going to break it into 4 equally sized rectangles, 4 divided by 4, which means that my width is going to be 1. We might use the notation delta x to also refer to the width, okay? The width of a rectangle can be called delta x because it refers to how much change in x value there is on each rectangle. So if I draw my orange left Riemann sums, I know that they're going to be 1 unit wide, and I'm going to use the left endpoints. Instead of I choose left or right, I'm going to choose the left side, 1, and that's going to be my rectangle. And I'm going to go across like this and come down. Now in the next interval between 2 and 3, since our intervals are 1 unit long, between 2 and 3, again, I think of that's my width, that's my delta x. I come up, left endpoint, go across, and then come down. There's my other rectangle. All right, and again, delta x is going to be the width of each one of these rectangles, delta x, delta x, delta x. In this case, they're all 1, and we just keep going. Draw the rest of the rectangles. And that is what's called a left Riemann sum. Now, unlike the first example, this left Riemann sum actually looks like it's a little bit more of an overestimate. But you could pretty easily find the area of those rectangles because it'd just be width times height. So in this left Riemann sum, I might say the area is approximately going to be 1 times, and what's the height of that rectangle? Well, I use the left side, so it's the function evaluated at 1. 1 times f of 1 plus 1 times f of 2 plus 1 times f of 3, and so on. It's essentially delta x times the function value, right? The delta, oops, I wrote x as I was saying it. It's delta x times the function value at that particular moment. And so remember, all these 1s come from the delta x calculation that was down here. All right, and I'm not going to take the time to plug that into my function up here. You can see that it'd probably be for x equals 1, it'd be 1 times, looks like 3 minus 1/12, so 2 and 11/12. And this one would be 1 times, and if you subtract, looks like 4/12, so it'd be 1/3, so it would be 2 and 2/3, and so on. You can go ahead and get all those calculations, add them all up, and you'd get some approximation. Now, let's talk about the right Riemann sum. If I'm using a blue rectangle, I'm going to still have the same delta x of 1, but when I make my decision to make the height, I'm actually going to go up to the right side and then go across and do the same thing for all of them. And you can see that now, instead of using f of 1, my first height is actually f of 2 on the right side. So this one area would be 1 times f of 2. So notice that's not f of 1 like it was on the left side, but because I chose the right side for the heights, I'm going to have f of 2, f of 3, f of 4, and f of 5, which is going to yield a different approximation. And you can see from my picture that the blue rectangles actually have an underestimate. I'm leaving some of that green highlighted area aside in between the graph and the x-axis. And again, you could use a calculator and add all these up. I'm going to move on to the next example in the meantime.